The focus of this video is to guide you to understand how you can solve Affine ciphers if you have the plain text message as well as the coded message. Affine ciphers require a key which one can find solving systems of linear equations. As we go through this video, you can see a way to finding the keys of a cipher. Again, this requires that you have the plain text message and the coded message as well. As we start, affine ciphers are ciphers that take the form of the equation y equals a times x plus b, where a and b are the keys that you want to solve for. Y is the coded message, and x is the plain text message. For example, we see from the example shown that my plain text message starts with the t, and the number that corresponds with t, the number 19, would be my x value. The coded message starts with an h, so my y value would be the number that h corresponds to, which is 7. The second letter in my plain text message is h, which has an x value of 7, and that coded is the letter b, which makes my y value 1. This is using the fact that the letter a in the alphabet starts with the number 0. You may have noticed how we could solve for a and b by noticing that we could use the first two letters and create two equations, so we could solve for a and b. This is where I want to start. I set up my two equations like you can see. For my first equation, I will use 7 equals 19a plus b in mod 26, and the second is 1 equals 7a plus b in mod 26. These are all in modulo 26 because there are 26 letters in the alphabet. Now if I solve my second equation for b, I would get b equals 1 minus 7a in mod 26. I can then substitute the b that I got from my second equation to my first equation. This is one of the methods for solving systems of linear equations. This would give us what I have here, 7 equals 19a plus 1 minus 7a in mod 26. Now I want to solve for a, so I could use algebra to go through this process. I could subtract 7 from 19 to give me 12, and that would change my equation to be 7 equals 12a plus 1. I then subtract the 6 over and divide by 12 so I can find what a is. You may notice that, though, that 6 divided by 12 is equal to 0.5. But I want to get a whole number, so I can see that since 6 is equal to 84 in mod 26, I can use that and the fact that 84 divided by 12 is equal to 7. So I know that a is equal to 7, like I can see here. We can then substitute that a into our equation for b to find our b value, and I've used similar logic for finding a to find b. I noticed that negative 49 is equal to 3 in mod 26, and then I was able to find that b equals 4. This process gives us a way to find the key to the affine cipher so that when we intercept another message, if the keys have not been changed since the last time we intercepted the message, we'll be able to know what the secret is. You may be able to get the treasure before they do, or you could save a life. Hopefully this helps to explain how you can solve affine ciphers without the keys by having both the plain text message and the coded message. If those are not given, and the key is not given, there are a finite number of possible combinations to try.